move on. Okay. So, yep. Okay. So, okay, so take a look at this function, right? We're going to talk about rational functions. So f of x is g of x over h of x, right? Where g of x and h of x are polynomial functions. So you've got one polynomial function in the numerator, one polynomial function in the denominator, no common factors other than one, okay? To graph this rational function, you have to find the zeros and the asymptotes. Just like I told you here, the first thing is the asymptotes, then we move on to the zeros, and that's how we're gonna graph this. Okay, so how do we find zeros then? To find the zeros, you have to set the numerator equal to 0, okay? So set the numerator equal to 0. For the vertical asymptotes, for the vertical asymptotes, you have to set the denominator equal to 0. Okay? So, for example, suppose you have y equals x plus 2 over x minus 3, right? To get the zeros, you just set the numerator equal to 0. That's it. That's the 0 of this function. For the vertical asymptote, x minus 3 equal to 0, x equals 3. Without having that information, especially with the asymptote, I wouldn't even attempt to graph anything. Okay, moving on. Horizontal asymptotes. How do we find a horizontal asymptote? If the degree, okay, so to find the horizontal asymptotes, now this is a different situation. What you have to do is, again, you have to treat the numerator and the denominator as separate function, and you have to compare the degree in the top with the degree in the bottom. What is the degree of a polynomial function?
2.
Well, in general, what is the degree of a polynomial function?
The highest degree.
The highest, another word for the highest exponent in the function. So in this case, what's the highest exponent in that function? A 1. What's the highest exponent in that function? A 1. You compare those two, and it's like a battle, right, between the two of them. So now there are 3 possibilities. The first possibility is the degree of the okay, so if the degree of the numerator is greater, then there is no horizontal asymptote. I am having some issues with my, okay. All right, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0, okay? And then if the degree of g of x is the same as h of x, then the horizontal asymptote is the leading coefficient of the top over the leading coefficient of the bottom. Okay, so let's take a few examples. So suppose you have, y equals x squared plus 3 over x minus 1. What's the degree on the top? 2. It's higher, right, than the degree on the bottom. So there is no horizontal asymptote. Okay. Suppose you have y equals x plus 4 over x cubed minus 2. Who has a higher degree? The denominator has a higher degree, so the horizontal asymptote is automatically y equals 0. And if the degrees are the same, oops. Huh? On the bottom, it's a 3. This is a 3. Okay. So suppose you have this. You see how the degrees are the same? all you have to do now is you have to say the horizontal asymptote is y equals the coefficient of the top over the coefficient of the bottom, so y equals 1. All right? Okay. Questions? Okay, so here are some examples of graphs of rational functions, right? Do you see how this one, there's clearly a vertical asymptote here? Here we have two vertical asymptotes and a horizontal asymptote, and then one of each, okay? Now, okay, I'll get you in a minute, okay. I want to clarify two things. First of all, whenever you state asymptotes, it always has to be x equals the number or y equals the number. So all of the vertical asymptotes has to say x equals, blah, blah, blah. Now, for the horizontal asymptote, this is where the book and I differ, and I do think I'm genuinely more correct than the book is. I don't want us to say for the horizontal asymptote f of x equals 0. I want you to say y equals 0 or y equals 2. Okay? All right, Daniel, did you have a question? Yeah. So let's go ahead and graph. Okay, so the first thing we want to do is find the asymptotes and the zeros. Why don't we start with the 0? So for the 0, we're going to set the numerator equal to 0, and we get x equals -2. If you're asked for the 0, get in the habit of writing it as a coordinate point, -2, 0. This is just the more elegant way of doing it, right? Because it is an intercept, right? It's an x-intercept. Okay, now, for the vertical asymptote, you have to set the denominator equal to 0, so x equals 1. And the minute I find x equals 1 is the asymptote, I like to just go over and do that. The biggest mistake students make is they confuse the vertical line with the horizontal line. So remember, if it says x equals 1, it crosses the x-axis at 1, right? When we say x equals 1, that means forever and ever and ever, x is always 1, okay? Now for the horizontal asymptote, we say x plus 2 equals, oh my God, sorry. For the horizontal asymptote, we're going to compare the degrees. Because they're the same, y equals, we compare the coefficients, y equals 1. Okay, so right here, y equals 1. All right, and let's go ahead and put that 0 there. At x equals -2, there is a 0. Okay, now we need to graph this function, and it's going to be the same process as graphing it, like in section 3, right? You can pick points, you can plug points in there, that always works. One thing that I also want you to be able to do is to find, I'll do that in green, to find the y-intercept. How would we find the y-intercept? You have to substitute a 0 for each of the x's. So for example, we say let x equals 0, which means we say y equals 0 plus 2 over 0 minus 1. So what's y? -2. So it's 0, -2. Okay, that always gives you a little bit of perspective. Sometimes I don't always ask for the y-intercept because sometimes it's too high a number. But you should always know how to find the y-intercept. Yeah.
Do we only still need 1 point?
Yeah, so now let's do one more point on the other side. Okay, so now let me talk about things like this, right? Because at the end of the day, I also want you to get away from the mundane plugging points in, right? So, in reality, all you really need to graph or to figure out how the rational function looks is 1 point. All you really need is 1 point. So right here, we found this 0 is over here, right? So I know that on this left-hand side, it's going to follow the horizontal asymptote. Then it's going to come down and follow the vertical asymptote here, right? And We also know from the chapter before, from the lesson before, from section 3, that if the graph exits on the bottom to the left of the vertical asymptote, on the right of the vertical asymptote, where is it going to re-enter, top or bottom? Top. It's going to come down here, and then towards the very right, it has to follow that asymptote as well. So there is really only one way for this to look, and it's just got to curve and look, like a rational function. Do you see that? This is what I need you to see. So really, all we need is one to get our orientation straight. Okay?
A question like that?
Huh?
Was it like a question? Tell us a sketch.
Oh, you will have to graph millions of these in this chapter. Yep. Okay. So why don't we, however, for completeness sake, let's just plug in one more point. Let's plug in x equals 2. So I get 2 plus 2, 4 on top, 1 on the bottom. So x is 4. And, right? And I'm sorry, y is 4. Yeah. Okay? So that's how that looks. Okay? All right. Now, you know how we said this enters or exits the screen on the bottom and then re-enters on top? Okay? Now let's think about this for a minute. Where did this vertical asymptote come from? What term gave us the vertical asymptote? The x minus 1, the denominator, the x minus 1, right? And, okay, so here we had x to the power of 1 minus 1, okay? Now that's important. Keep that in mind. Okay. Take a look at this one now. Here we have x minus 1 over x squared. So quickly, let's find the 0. What is the 0? Right, 1 comma 0. Okay, what is the vertical asymptote? So now we're going to do x squared equals 0. X is 0. So here and here we have a vertical asymptote. All right, what is the horizontal asymptote? You have a 1 here and a 2 here. Higher degree on the bottom means y equals 0. Okay, now a couple more things. The vertical asymptote comes from the point where the denominator is equal to 0. That means the function there is undefined. There is no way the graph can ever cross the vertical asymptote. The graph just simply cannot exist at that point. Okay, technically speaking, the horizontal asymptote is a different situation. You'll learn in future years that the horizontal asymptotes really only take effect at the ends of the graphs, at the infinities. So at positive infinity and at negative infinity. In reality, if we were able to really see a horizontal asymptote, it would look more like this, where there's no horizontal asymptote in the middle, it's only on the sides. You're never allowed to draw it like that, okay? But that's how it looks. So don't draw this, but we can never cross a vertical asymptote. However, if there was a horizontal asymptote, a graph can cross a horizontal asymptote 1,000,000 times, but then it levels off at the infinities, okay? Because by definition, the vertical asymptote is like the end behavior at the infinities, all right? Okay, that's an important point. Okay, so what is the y-intercept here? There is no y-intercept because x can never be 0, okay? So, no y-intercept. Yep.
How is the horizontal asymptote, if you're just looking at an equation, how is it different when x is a smaller number versus a bigger number?
So it doesn't, because by definition, the horizontal asymptote is what happens as x approaches infinity or negative infinity. And when x is infinity and negative infinity, only the higher degrees count. So for the horizontal asymptote, we don't even look at the bottom number, the smaller numbers. Okay? It doesn't even exist in the definition. The horizontal asymptote really only exists here. Okay? Okay, more about that next year. Okay, so here's what we're gonna do. Let's put some numbers in here. So why don't we put in, okay, so we know there's the 0 there. Why don't we put in x equals 2? What do we get when x equals 2? We get 1/4. Oh, here. So it does cross the horizontal asymptote there. You see that? What about when x equals 3? We get 2/9, right? Is 2/9 bigger or smaller than 1/4? Smaller, so now it goes back down. Okay, what about when x equals 4? We get 3/16. That's even closer to 0. All right? Okay, so what about when x equals -1? Then we're going to get -2/1, which is just -2. And why don't we just put in -2 as well? I just want to show you guys how this looks. So -3 over what? 4, is that right? Here. Now, okay, now look. So here, this graph, it looks like it's going to follow the asymptote like this, the vertical asymptote. It goes up, hits that point, but now it's going to come back down, and now we're at this point. Now, does this function have any other zeros? No. So it is never allowed, so it'll never cross the x-axis again. That means once it gets here, it's now just going to follow that horizontal asymptote. Okay? But wait, we knew that when the graph exited on the bottom here, it always re-enters from the top. But how come we have points on the bottom here if it can't cross the x-axis again? Well, that comes from here. You know how here it's x squared equal to 0? That's a double root. Remember when we learned about repeated roots or double roots, right? Because it's a double root like that, over here, it keeps on the same side. So it re-enters on the same side and goes over here. Okay, so it's going to re-enter on this side and go this way. Okay? All right, questions? That was a tough one. All right, so let's take a look at this one. Okay, so for the 0, set 5 equal to 0. Does that even work? No. So no zeros, which is okay. Okay? All right, so for the vertical asymptote, we say x equals 1, x equals 4. 2 of them this time. Okay? Oh, thank you. It's here. All right, what's the horizontal asymptote going to be? What is the degree on top? On top? 0. What is it on the bottom? No, because it's x to the 0. It's 5x to the 0, so it's just 5 times 1, which is 5. On the bottom, though, when you multiply this out, it'll be x times x, x squared. So the degree on the bottom is 2. Okay? So here we have degree of 0. Here we have degree of 2. So the horizontal asymptote is y equals 0. Okay. Now, okay, so now we have 3 regions. We have to have a test point in one of the regions. Why don't we get a test point at where? Like x equals 0. All right, when x is 0, what do we get? 5 over 1 times 4, right? 5 over 4, is that right? when x is 0, we get 5 over negative 1 times negative 4. Okay, so that is 1 1/4 here. Okay, so look, we're going to try to do this whole thing without even plugging in a different point, another point. Are there any zeros here? No. So the graph will never cross the x-axis. Now look, it's on here. It's on the top at x equals 0, right? So it's got to go up this way. And then here, it's got to follow the horizontal asymptote that way. Now, go over to this asymptote. What is this asymptote? X equals 1. Where did we get x equals 1? Here. Is there a double root situation here? No, right? That means it will alternate positions and it will re-enter on the bottom of this. Okay? So it's going to re-enter here. Now, so when it comes up here, what's it going to do? Can it cross the x-axis? No. That means it has to go up and somewhere come back down. Okay? Now it's down here. Where did this x equal 4 come from? Here. Is there a double root situation here? Double root. So remember, okay, so for the other one, I had x squared equals 0. Okay? And what does that mean? That means x is 0, x is 0. Yeah? But at x equals 4, there is not a situation like that, so it's got to re-enter from the top and go over there. Okay? So that's how you can do it with no points being plugged. Now, if you wanted to plug in points, is anybody going to take points off? Haha, points off. No. You plug in a 2, you get negative 5 over 2. You plug in a 5, you get 5 over 4. And so you know that it's supposed to turn around. Yeah.
When do you know, like, when the upside down parabola, like, stops?
So you have to plug points for that one, but it's okay for me if you just kind of eyeball. You just can never touch the x-axis if there are no zeros. All right? Okay. Did you ever think you would be able to graph something like that by hand without a calculator? Look at how far you've come since last, like, August. Do you see that? Yep. Another asymptote, and that's called the oblique asymptote. So let's go to the next page. Oblique asymptotes. Oblique asymptotes are also, they are used to be called slant asymptotes. They're basically, diagonal lines like this, okay? So, remember how we said if the degree of the numerator is higher, there is no horizontal asymptote? That is always true. However, if the degree of the numerator is exactly 1 greater than the degree of the denominator, then there is an oblique asymptote. So if it's x cubed over x squared over x, right? 1 higher on top, then there is an oblique asymptote. How do we find the oblique asymptote? Polynomial long division. You have to divide the polynomial. Okay? Yep, you remember polynomial division? It's back. It'll never leave you. Okay. So, the oblique asymptote, when you do the division, is the quotient without the remainder. So you throw away the remainder and it's just the quotient. So here, the vertical asymptote, right? X cubed equals 1, x equals 1. And then when you divide, the oblique asymptote is y equals x plus 3. And you just graph it algebra 1 style, and that's your asymptote. Okay, let's do it 1 here. Okay. X squared. Okay, so what is the 0 here? What do you guys think? X equals 0. Okay, vertical asymptote. X equals 2. Horizontal asymptote, none. So it's either going to be horizontal or oblique. You can't have both, okay? Because it just doesn't that doesn't work. Now, the oblique asymptote. Let's do the oblique asymptote. you're going to divide x plus 2 into x squared. Okay? But now, so you guys remember how to do this? So this over this, what do you get? X to the 1. So here we're going to add a plus 0x. So I get x squared plus 2x. Change the sign. So we get negative 2x. Add another 0 here. Bring down the 0. Now what do we get on top? Negative 2. Negative 2x minus 4. Change the signs. And we get a remainder of 4. You literally throw away the remainder of 4. We don't care about the remainder. What you get here is your oblique asymptote y equals x minus 2. Okay? So let's graph all these things. So x equals 2 is the vertical asymptote. There is no horizontal, but then x minus 2, how do we graph x minus 2? There is a point there, up 1 over 1, literally algebra 1 style. That's the oblique asymptote. Okay. Let's plug in some points here. What point should we plug in? Let's plug in a 3. You know how it's y equals x minus 2? You do y equals mx plus b. Y-intercept is negative 2. Slope is 1, so you go up 1 over 1. Okay, so when you plug in 3, what do you get? Oh, you just get 9 over 1, which is 9. So when x is 3, y is, 9 all the way up here. Oh my, okay. See, like they tend to go up very quickly. Okay, so what about when x is 0? Oh wait, I didn't put the 0 in here. Okay, so now take a look at how this works. Function is going to follow the vertical asymptote up there, come back down, but now, are there any zeros on this side? No, this will never hit the x-axis, but it's got to follow this somewhere. So it's going to turn around and follow that oblique asymptote here. Now, let's go over to this. It's all about the vertical asymptote. Let's go over to the vertical asymptote, right? Wait a minute. Wait a minute. Did I do this correctly? All right, so now that we fixed our asymptote, let's do this again. All right, so it's going to be y equals x plus 2, and then up 1 over 1 here, so that's how it looks. Okay, but this is still the same, right? Because it's going to look like this. Okay? But now, again, this looks much better. Whew. Okay, this exits the screen on the top. Where would it re-enter? On the bottom here. On the bottom, hits this and comes back down. Okay? Man, that is a beautiful function. Isn't it? Yeah.
If the numerator is greater than the numerator, which is greater than the denominator by 2.
There would be none of them, just.
So it's only like the linear.
Okay. Yeah. Okay, last little bit here. Is a point of discontinuity. Okay, so we talked about vertical asymptotes, and vertical asymptotes come from when the denominator is set equal to 0. Okay, now there was one thing that I didn't mention, which was the following. When you're setting the denominator equal to 0, you first have to see if you can simplify the function and cancel any terms out, okay? So, when the numerator and denominator have a common binomial factor, then there might be a point of discontinuity. That's the technical term. The way it looks is there is just a tiny pinhole in the graph. And this is an important thing to notice. Like literally when you take a pin and like you puncture something, you can barely see it, right? That's how tiny that hole in the graph is. We exaggerate a little bit when we're drawing, but it's a tiny, tiny little puncture in the fabric of this function, okay? And this is another point where the function is undefined. So now let's take a look at how that looks. Look at this function. Do you see how I have x squared minus 4 on top and x minus 2 on the bottom? Well, the minute you see the x squared minus 4, you should know that, wait a minute, I can factor out x squared minus 4. Okay? Now, the minute we had seen this, we also knew at x equals 2, something bad happens, right? X can never equal 2. But when we factor, you see that, wait a minute, the x minus 2's cancel, right? So what we thought was going to be a major problem at x equals 2, I'm now able to cancel it, and I'm able to remove that problem. Because I'm able to remove that problem, all right, it's no longer a vertical asymptote, now it's just a hole in the graph. In the future, you'll see that it's also called a removable discontinuity, okay? So, we're going to say there is a removable discontinuity at x equals 2. So what's the, simplified function now? It's just x plus 2. Do you see what we did? The simplified function is x plus 2. Does it have a vertical asymptote? No. The discontinuity that appeared here, we removed it. That's why it's a removable discontinuity. The vertical asymptotes are infinitely there. They're called infinite discontinuities. So now, how do we graph this? My function reduced to y equals x plus 2. So now I'm going to graph y equals x plus 2. However, at x equals 2, there is a hole in the graph. So let's graph this. How would it look? Y-intercept, up 1 over 1. There is another point. Okay. Now if you go up 1 over 1 again at x equals 2, you would have had a point there, but now you have a hole in the graph there. So the way we graph it is like this. Okay? So many things. Right? Okay. Let's take a look at this one. Oh no. Okay, so let's take a look at this one. Yep. Okay. Okay, so take a look at what happens here. Oh, take a look at what happens here. X plus 2's cancel. Does the x minus 3 cancel? It does not. So this reduces to x minus 4, x minus 3. So there is a removable discontinuity at x equals negative 2. You know how the x minus 3 never went away? That is a vertical asymptote. Yes. There is a vertical asymptote at x equals 3. What is the horizontal asymptote? Y equals 1. What is x equals 4? That's a 0. Good. Okay, so at x equals 4, there is a 0. Y equals 1 is a horizontal asymptote. X equals 3. Okay? And then, okay, so look, here on the right-hand side, we know it's going to come over like this and down. Yes? Now, on the left-hand side, is it going to re-enter from the bottom or the top? The top. Okay, so now look, guys. At x equals -2, there is a removable discontinuity. So how do we know where on that line it is? Like, is it here, 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 here? How do we know where it is? So here's what you can do. Mentally, do not ever write this down. Mentally, just ask yourself, if I were to plug -2 in here, what would I get? What would that give you? -6 over -5, right? That's 1 and something, right? That's around where the removable discontinuity is, because it would have had a point there, but now there is a removable discontinuity. We can never show us plugging -2 in there, however, because technically it's undefined there, right? We just do it for like technical purposes, okay? Don't ever get caught plugging in, you know, a value at -2, okay? And there it is. Okay, and if this is not the most beautiful thing on the face of the earth, then actually, I don't know what is, right? I don't know why you're not as excited about this as I am, but like, this is like the most amazing thing on the